Continuing from previous lecture, in which we did the 2's complement method and we converted a 2's complement number or a binary number in 2's complement format, whether it was positive or negative, to a decimal format. We did a really long computation to figure out what that number was. We actually added minus 2.1 billion and then we added 1 billion and so on and so forth. Actually, there is another way of doing it. Let me demonstrate that. One way which I explained in the previous class was that, let's say if you want to convert this number to decimal, what you can do is, if it's a really large number, you can take the 2's complement of this number again, and which is inverting all the bits and then adding 1, and then you will find that the actual number would be plus 6. That means the original number of which we took the 2's complement was actually minus 6. There is another way of doing it. Let's say if we have all ones and the most significant part. Let's say if we have a number 1010 and let's say we only have a 4-bit number, which means that the placeholder, it is 1, this thing is 2, and this thing would be 4, and this thing would be minus 8. And let's say we only have a 4-bit number, so if we add minus 8 plus 2, the bits which are activated, we get minus 6. Let's say if we have this number 1111 and 1010, this number is actually also equal to minus 6. Let me demonstrate that. Because all the more significant bits from this number onwards is actually 1, so that means that the value of this bit would be, let me demonstrate that. Let me write it in a wider format, 1111 and 1010. The placeholders would be 1, 2, 4, 8, 16, 32, 64, and this bit would be minus 128. So that means I need to add this bit, and this bit, and this bit, and this bit. Let me get the calculator, or we can do it right here. So if we add minus 128 plus 64, we get equals to minus 64, and then we add 32 to it, we get minus 32, and then we get plus 16 to it, we get minus 16. So that means that, and then we add 8 to it, so we get minus 8, and then we the same thing which we got over here. And if we add 2 to it, so we get minus 6, the same result we got. So that means that if we have these numbers and all the bits are essentially, what we have is actually a 16-bit number, even then it will make no difference. So that means that you can ignore these bits, you can ignore all of these bits, and then just take just add this number. I mean, because this condition only applies when all the bits, all the more significant bits are 1. So 1, 2, 4 and minus 8, just consider these values. Minus 8 plus 2 would be minus 6, and that's it. You can just ignore all bits. The reason why this thing actually works is, if you take 2's complement of this number, if you take 2's complement of this number, you will get 0 0 0 0 0 0 0 0 0 0 0 0 and 0 1 0 1, and just to add 1 to it, so you will get 0 1 1 0, which is actually equals to 6. That means the original number is actually minus 6 over here. So the reason why this trick actually works is, if you take 2's complement, you actually ignore all these zeros because they don't contain any value. Similarly, if you are just adding the placeholder values like we did over here, or you can do it if you want to do go all the way to minus 65535 all the way to 65531 65536 all the way over there. What you can do is, if you take it that all the bits here in this going in this direction are 1, so you can ignore them, and you can just say that this bit is minus 8 and just add them together if you want to do it. It doesn't come that often in exam if you want, because this binary to decimal or decimal to binary conversion is wholly for the understanding that how these numbers are represented in computer, and computer actually represents the negative numbers as in 2's complement, so for easier addition and subtraction, because subtraction then becomes addition if you represent the number in 2's complement format. Okay, so another thing, or just continuing now to the new topic in this lecture, let's go to our original file. Here we were discussing the fundamental types, and we discussed the Boolean enumeration character types, and now we were discussing the integer types, and we discussed the ranges of these numbers. So what I'm going to do is I'm going to demonstrate that what are the size of these numbers are there in my computer, and it might be dependent on you that if you are using some other version of the compiler, or if you are using an operating system which is different, then it might be possible that the implementation would contain different sizes. So I'm using Windows, and it's a 64-bit operating system. That means the address bus is 64-bit wide. And let's see if what we get over here. I'm going to declare the variables, and I'm going to see their sizes, what their sizes are. And once I know their sizes, I can figure out the range or the maximum number that variable can store. And then I'm going to demonstrate that what if I exceed the range of those variables, then we have an overflow error, which is a runtime error. It will not be shown at compilation time, because the computer will just cycle around to the next value. I'm going to demonstrate that in the code. So let's write the code over here. This was the file in which we were discussing all these ranges over here, and if we exceed the range, and we'll see what will happen. So let's type a new file. So I'm going to make a new file, Control N. I'm just going to write the basic structure, include IO stream, and using namespace standard and integer main void, and the last line would be return 0 for successful completion. And what I'm going to do is I'm going to declare the variables of these types here. I'm going to declare I think we did the Boolean type as well. Let's see, just to make the size of operator and figure out what size there is. So I'm going to declare Boolean character, and then I'm going to declare short, integer, long, unsigned short, unsigned integer, unsigned long, and then I'm going to declare long integer, and long integer, and so on and so forth. So I'm going to pause the video, or I'm going to declare all these types, and then I'm going to see what their sizes are. Alright, so let's just type the code. Actually, I did pause it, but it's actually better to demonstrate it as we type along. So I would suggest you type along as well as you are watching this video. You can just watch this video on your mobile phone and type on your computer if you want to. So I'm going to declare Boolean variable b. I'm not going to initialize it, but I'm just going to declare it because I want to figure out what the size of that variable is. And enumeration type, well, they are just integer constant. I'm going to declare character c, and then I'm going to declare short, just to remember, is short s. It's actually a short integer. And if I did not write it, let me demonstrate that. Short, then I write integer I, and then I write long integer I, then if you want, then long, not a, sorry, I cannot have this over here, so just a name, and long integer li, just a name. And if I write unsigned short, you can just have any name over here, no problem with that. And you can write unsigned integer ui. And what are the next types? And unsigned long integer. Okay, I can have unsigned long integer and unsigned long integer, and so on and so forth. Okay, I do not need to write signed over here because this thing is redundant, because whenever I declare an integer, it is a signed integer by default. If I write an unsigned integer like over here, so that means the value will go from 0 to the maximum value. But if I write signed integer or do not write signed integer, it means exactly the same thing. So let's check whether we have what's the last example I did over here, example 18. So let's write this thing as example 19.cpp, and there is no, hopefully there is no error. Okay, so I'm just declared those variables. I did not see out anything. So what I'm going to do is I'm going to see out these statements, see out size of bool is, and I'm going to write size of. It's a function which just returns the size in bytes of that object. In this case it's b, which is the boolean variable. I'm going to write and l over here. So I'm going to copy this whole thing, and actually I'm going to copy this thing over here. 1 2 3 4 5 6 7 8 9 10. So we have 10 lines. And let's copy this thing. So the names are B, and here is C, S, I. I'm going to type again over here what that thing is. I'm just going to figure out what these sizes of these objects are. US, UI, ULI, and ULI. I think that's it. I think we, and C is character, so I'm going to write character is for easier reading, and short integer. I think you do not even need to write. Okay, I did not write short over here. Actually, it's short means short integer over here. I could have written short int as and then declared it. Integer, which is assigned integer, long integer, and long integer for easier reading actually, and unsigned short. I mean, it would have the same size as short, but the range would go from 0 to positive number, not from minus negative, I mean negative minimum to positive maximum. Unsigned integer, and here finally unsigned long integer, and unsigned long integer. Okay, so let's run this thing and see what we get. So size of boolean is 1. That means that boolean is an integer which it is only allowed values of 1 and 0 or true and false, and it is of 1 byte. So size of character is also 1. Size of short integer is 2, and the normal signed integer is 4 bytes. Actually all of these numbers are in bytes, and long integer is also 4 bytes. So no difference between these two as far as this implementation of C++ is concerned. Long integer is 8 bytes, so it's a really large number, and unsigned short is 2, so no difference between the size occupation of this short. Here is 2, and here is also 2. Only difference is that this short integer can contain negative values, but this one cannot. And unsigned integer is 4, the same size occupation as here, but this integer can only contain positive values. Same thing is, I mean, no difference between long integer and integer over here as far as this implementation is concerned. And unsigned long integer is occupying 8 bytes, but it can only contain positive values. Now we know the size occupied by each of these objects of fundamental types. We can now see what will happen if we exceed the value which can be stored in these bytes. Let's take an example of a simple example of short integer. Short integer, the size occupation is actually 2 bytes, so that means I haven't written signed, so it's understood to be signed here. If I've written unsigned, that means it can only contain from 0 to positive maximum value. Here it's assigned, understood to be there, so it can contain from minus negative some value to positive value. Let's figure that out. So if I make a new file, I'm going to make a new file over here, and I'm going to copy this whole thing just to write the structure over here, and I'm going to delete all of these things. So I'm going to declare a unsigned just to make it simple. Unsigned short, just to write name a equals to 50. A is the name of a variable or an object. The type of that object is unsigned short integer, and it can only contain positive value. If I need to figure out what those values are, I just need to include I'm not going to use any of those things. I mean C limits, and if I press Control and this cursor becomes a hand, I press this thing, then I go to limits.header file, and there we have it. So unsigned short maximum goes from 0 to 4f. So 4f means 16 ones, and if you can just, I mean it's a 2-byte number, so it can go all the way to, let's take a calculator, to 2 to the power 16. So that will be 65536 are the maximum combinations, going from all zeros to all ones, and the maximum value would be 65535. I mean it's very similar. If you are counting from 0 to 9, you have 10 numbers, but since you are counting 0 as well, the maximum number would be 9 and not 10. So that is the maximum range of the unsigned short number. So had it been assigned short and integer, the maximum value would be 32767, and the minimum value would be minus 32768. Now coming back to our example, this thing I'm just going to write cout value of a is, and the value a, whatever the value is, and L, and the size I've written that already. So size of a is, and size of a and L, and just figure it out whether it's running correctly or not. The last file is e19820.cpp. extension is important, and we see that value of the size of a in bytes is actually 2. It's occupying 2 bytes, and it's an unsigned, so we can only contain positive values. So the maximum value is 65535. So if I just write 65535, I already know the size, so just remark this line and see if we are getting 65535. There we have it. Now that's the maximum value we can store in 16 bits because it's an unsigned short integer. So what I'm going to do is I'm going to do a equals to a plus 1, and I'm going to see out this thing. Value of a is now a and L. So let's see what we get. Now the original value was 65535. I added 1. Now the value is 0. And let's do another example. A equals to a plus, I mean this thing is 65535 plus 1. It should be 65536, but it cannot do that. The effect is really similar if you have I mean if you have a distance meter, which we call the trip meter in cars. I mean we have trip meters in cars, so let's take an example. What will happen if we have I mean, you can do it over here. So here, so trip meter, if we have a trip meter which counts the kilometers, actually we have right now we have such a large trip meter going from 0 to a million kilometers. So I mean it's really unlikely you will see the cycling around effect. But let's see if we have a trip meter which can only store from 000 to 999. and it does not have any other number over here, so it can store from 0 to 999 kilometers. And let's say we have driven the 1000th kilometer from 0 999 and then we go to 1000, it will cycle it back to 000. And that's exactly what has happened over here. I mean, we will store a 65535 over here in the unsigned short, and then we added another 1 to it, so the next value would be like this. So the next value would be all zeros, because it will cycle down to all zeros, and the next significant bit, it would be incremented to 1. But since it has only 16 bits, it did not have this bit, so that means this variable is now carrying the value of all zeros. So sorry, it will be another 0 over here, so this thing would be like this. So this the number can only contain 16 bits, so this thing will cycle back to the initial value, just like as the trip meter in our cars. If you have driven, I mean, I've seen cars in which the older cars in which the trip meter goes from all 5 zeros to 999 and 99. So if you're driven like over 100,000 kilometers, it will go back to 0. So I mean, just the whole meter just repeats itself over and over again. So it's in old cars. I think in newer cars the trip meter goes from 0 to maybe 1,000,000 kilometers or 999,999 kilometers, and then it cycles back to 0. Not so sure about it, you might want to check it out. But that's what is happening in this cyclic effect whenever we are exceeding the range of this thing. So let's do a plus, for example, 2. So I'm expecting it should show 1 over here. That's what we have over here. So 65035 plus 2, I mean, it will go to 0 and then to 1, so it's keep on cycling itself. So if I just write 10 over here, so it will show 9, because 65535 is the maximum number which we did store. Then we added 10, so it goes to 0 1 2 3 4 5 6 7 8 9, so we added 10 places. It does not have the 17th bit to carry that most significant bit, so that is known as an overflow error. So I can demonstrate another example, which is some number. Let's say integer a equals to, for example, 10, and then I write a equals to, let's make a big number. Integer is, size of integer was, I think, size of integer, let's run this program again. I think it was 4 bytes. It's a signed number, so size of integer was 4 bytes over here. So 4 bytes means that it will go from, it's a signed number, because I did not write signed over here. I mean, it's understood to be signed. You can just write signed over here as an identifier, but it's not necessary because understood to be signed. If you want to have an unsigned number, then you need to write the signed over here, unsigned over here, sorry. So that means that it's a 4-byte number, and 4-byte number means we can go to limits and see what we get over here. What are the limits here? So integer minimum, so it could go from -2 point some billion to +2 billion. So that means it's a signed number, or had it been an unsigned integer, it would go from 0 to 4 point some billion number. I think we computed that in the previous lecture. So let's say that we have 1 million, and then let's see out this thing. See out, and value of a is a and L, and then just run this thing. Oh, there's a problem. I think I've declared the variable a over here, and I cannot reuse that same thing, so my mistake. So value of b, so just rename this thing. Value of b, it shows 1 million. I think let's remark the whole line, so I'm just dealing with these things only. So making a multi-line remark over here, value of b. So what I'm going to do is b equals to b multiplied by 1000. So that means 1 million into 1000, b would now be, so let's copy this line, is now, and let's see what we have here. So originally it was 1 million, now is 1 2 3 4 5 6 7, now it's 1 billion, and we know that the maximum number is minus 2 point some, sorry, the maximum number is plus 2 point something billion. So I'm going to again b equals to b into 1000. So the calculators would show that if I use a calculator and I multiply million with 1000, I got 1 billion, which I which was displayed when we ran this code. And if I again multiply this number with 1000, I should get 1 trillion. So 1 2 3 4 5 6 7 8 9 10 11 12 zeros. But this integer cannot store more than 2 point some billion number. So let's see. I'm going to copy this thing and I'm going to see what we get over here. There we have it. So 1 million originally 1 billion was within range, then it cycles to some number, and if you want to count, it will go all the way to negative, then go to all the way to, I mean, it would have cycled multiple times so to arrive at this value. But this value is wrong. This value is known as overflow error. It's a runtime error. It's not a compile time error. I mean, had we made some kind of a syntax mistake, just like we did here, that I named this variable as a, and a was also made over here when I wasn't commenting this line. So I can now make this variable as a, no problem at all. So because a is not visible to the compiler, but it was originally it was an error. I cannot have a variable and then redeclare that variable with the same name, because that has already been named. So that was a compile time error whenever we are making some syntax errors. This error is a runtime I mean, it's not even a runtime error. It's not even showing these runtime errors. It's just showing the values. But these are actually these overflow errors. I mean, they can happen. I mean, you have to keep in mind whenever you are dealing with the variables, and you have to keep in mind what values would be there. So if you're taking the input from the user and the user really inputs a really large value, you need to check it out whether the value actually exceeds the limit of your variable size, because if the user has input a very large value and your variable cannot store that very large value, you will have an overflow error, just we have demonstrated over here. And if you use that wrong overflowed error value in some further computation, those computations would also be wrong. So some kind of a compounding error would happen without anyone realizing that what was the original problem. So it's really important to check whether the input values or whether the values which are being generated at runtime should not or must not exceed the storage limit of these variable objects. So that's the demonstration over here, and you need to keep in mind that if you exceed those values, you will have some erroneous values over there, some values which contain error. And if you're using those values in computations or calculations later on using some kind of formula or anything, the results of those computations will also be wrong, because the seed value is actually wrong. So you have to keep in mind that it should not exceed or must not exceed the limitations of these sizes. So if you are expecting a really large value, so I would suggest you go from long integer is same, so you just do long integer. And because this thing can have 8 bytes over here, so 8 bytes is 64 bits, so to the power 64, I think we saw that it was something like 19 billion trillion kind of a number. It's a really large number. So let's see if we have but even then it's a finite value, so let's see if we are getting the right value over here. So there we have it. So 1 million, and now is 1 billion, and now it's 1 trillion. So we can have these values here. I mean, I could just multiply it with I mean, and it's a signed number, right? So let's try exceeding this as well. So I need to figure out 2 to the power 64 is 18. 1 2 3, let me count it down. 1 2 3 4 5 6. Can I view with No, I cannot, sorry. How can we display the commas? Okay, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18. So it's kind of a 18 billion billion, so 18 billion billion. Okay, so this was 1 million, this was 1 billion, and this was 1 trillion. So if I multiplied with again, if I multiply this thing, let's repeat this thing. 1 trillion, so it was billion billion, so it was kind of 18 zeros, so not 12. So I can only multiply with maybe a million. So let's see what we get over here. F11, and there we have it, no problem at all. But if I multiply this thing with a billion, now it is showing under some wrong value, because this thing is cycling once again, exceeding the range, and is showing some long value. So whenever we are dealing with some really large numbers, we will discuss a floating point type, in which we can lose some of the precision, or if it doesn't contain any decimal part, we can just use the exponential format of floating point numbers to represent extremely large numbers if you want to. But here is just demonstrating that we are having some kind of an overflow error if we exceed the storage capacity of these variables. Just to summarize what we have done so far, we have discussed the size of these variables and the storage capacity, and we did the another way of computing the decimal equivalent of a number which is represented in 2's complement representation. In the next lecture, we are going to do some arithmetic operators, and we are going to do some floating point numbers in this thing. This thing continues, and it will be concluded, and we are going to discuss these sorry, here we are going to discuss these floating point numbers, as well as double and long double for double precision floating point numbers. So it will have some decimal part as well as for the exponential part to represent some really large numbers. But keep in mind that this thing can represent a really large number, but it has finite precision, so it might have some kind of a round off error. Here we have an overflow error. There we could have overflow as well as a round off error. We need to keep that in mind. We're going to discuss that in future lectures. The summary of this lecture is that we did the 2's complement shortcut, and we did the size of operator, which outputs the size of the variable or object, or maybe an expression in the round brackets in bytes. And we also saw a very important topic of which is known as overflow error. If we exceed the range of the or if we exceed the available range of that variable in terms of integer, that will cycle back to the initial value, and it will go, I mean, I have explained that in this lecture. So we need to keep in mind that if you are storing some really large values, we have to keep in mind that what kind of integer we are using to store that value, and if that really large value actually exceeds the range, so obviously we have an error. And if you are using that value for some subsequent calculations, obviously there will be some compound errors in there, or those overflow errors are essentially runtime errors. They are not compile time errors, because we did not make any syntax error, or we did not make any error which could not be compiled by the compiler. These are the actually overflow errors which actually happen during runtime, depending on whether the user has input some very large value which we are storing in the variable which cannot hold that large value. So that can give rise to the overflow errors.